السلام عليكم ورحمة الله وبركاته. Today we'll continue our lectures. Okay. Let me put it in the presentation mode. I hope it is going to work. I have started considering, the different methods or transport mechanisms, contaminant transport mechanisms. Okay, we looked at the dominant one, which is advection, which behaves like a clog flow, where the contaminant is carried, or where it is assumed that the flowing fluid moves with an average forward velocity, and so all the contaminants move with the same average forward velocity. Okay, and then we have dispersion, which is more realistic because it takes care of the spread caused by the variation in the velocity, okay, at different regimes. Okay, and we looked at the dispersive flux as well as the advective flux. Now we are looking at the diffusive transport, okay, where we said is dominant if the fluid is static. It also occurs in flowing fluid, okay, and in moving fluid, advection and dispersion are the most important processes, while for static fluid, diffusion is the most important transport process. Okay, and when flow velocities are very low or the bulk fluid motion is absent, diffusion is the most important contributor to transport. I hope you can see the next slide. Can you see the next slide? Let me check your responses. Okay, so that's fine. So let me go back to my slide. The presentation mode. Okay. This we explained before. Okay, when you have the mass, for advection, it moves undistorted. Okay, because we assume that all fluid particles at a given cross section have the same forward velocity. Okay, this is for advection alone. When we include dispersion, then our contaminant becomes a little bit distorted because of the fact that the forward velocity, if this is solid boundary, this is open to the atmosphere, then the velocity increases, maximum at the top, minimum or zero at the bottom. Okay, so that will affect the shape of the contaminant. Okay, because some particles will move faster than others. Okay, then when we include diffusion, okay, it becomes more distorted. Okay, this will include all the three transport mechanisms. Okay, advection, dispersion, and diffusion. Okay, so it becomes the contaminant becomes more and more distorted because now you have many other processes taking place or that are affecting the movement of the plume. The plume is the contaminant, within the water. Okay, and then you have the concentration here. The concentration here, because we assume it's moving like a plug, so it's constant. Okay, this is the concentration. Okay, with time, okay, is the same. Okay, but then when we include dispersion, initially, because water moves, you have to wait until you begin to record the contaminant. And then the concentration at this point is zero, then it increases to maximum, and then it decreases. So that's why you have this bell shape. Okay. Then when you include advection, it becomes flattened out. Okay? It becomes more and more flattened out. Okay, meaning the concentration the maximum concentration recorded is lower in this case because contaminant becomes more and more spread. It's spread within the flowing fluid more and more, okay? Unlike in the case of advection alone, where when the concentration remains the same and it moves like a plug, okay? Like being pushed, like something solid that doesn't mix. It doesn't, for advection, it doesn't take care of the mixing effect of the contaminant with the flowing fluid, okay? While dispersion and diffusion takes care of that mixing effect as a result of velocity gradient and concentration gradient. Okay. I think we already did this for the advective flux. Look at this example. Now, for the diffusive flux, we use the fixed first law of diffusion, which states that the diffusive flux is equal to minus d times the concentration gradient, meaning that the flow is towards areas where the concentration is decreasing. Okay, the negative sign here indicates that transport is in the direction of decreasing concentration. As you move along the flow field, the concentration is decreasing. It becomes more and more less. Okay, this is the mixing due to the mixing effect. And D is the coefficient of diffusion or diffusivity, and its dimension is L squared over T. Diffusion coefficients in a porous medium are smaller than in pure liquid medium because solids hinder diffusion. Okay, when you have, let's say, a pipe in which water occupies, the whole cross section. When you have another pipe, but with solid matrix, porous medium inside, okay? So the porous medium will affect the extent to which diffusion occurs, okay? So that's why we're saying that the diffusion coefficient, because the higher the diffusion coefficient, the more the transport is affected by diffusion, okay? The porous medium, okay, affect the extent of diffusion. When you have a porous medium, okay, so it's usually smaller than in pure liquid. And to obtain diffusion coefficient for a porous medium from a diffusion coefficient of liquid, a constant factor of less than 1 is applied to account for the porous medium structure. Okay, and the constant factor is a function of both porosity and tortuosity. Explained porosity and tortuosity before. Tortuosity is the tortuous path, the irregular path taken by fluid, okay, in porous medium, because unlike in liquid, in which you have pure liquid medium, where the liquid fills all the space. In case of porous medium, you have the porous medium grains fill most of the spaces, and then the tiny voids or spaces in between the porous medium is one available for fluid to flow. Okay, so that creates like a regular path, the tortuous path through which liquid can flow. Okay, so all this affects the diffusivity or the diffusion coefficient when you have porous medium. Okay? So this is exactly why we started in the previous class taking this example where we have a methane in a landfill. You know what is a landfill from CE 330, environmental engineering. You will design landfill where you dump your waste by compacting them in layers. Okay, you find a very vast area of land. You take your waste, solid waste, and be compacting them in layers. Okay? Normally, you have a liner, so that it doesn't affect the groundwater because sometimes you may have leachate. Okay? So methane concentration in a landfill at a depth of 3 meters is 20 milligram per liter. Atmospheric concentration, that's the atmospheric concentration of methane is 4.87 milligram per liter. What is the rate of transport of methane from an acre of landfill? Okay, diffusion coefficient is 4.0 times 10 power minus 6 centimeters square per second. Okay, methane is a gas, isn't it? CH4. Okay, and it can diffuse. Okay, it can move from the landfill. Okay, concentration at a depth of, you have, let's say, a landfill. Let's say this is the landfill. Okay, and at a depth of 3 meters. Let's say this is 3 meters. Can you see the slides?
Yes, doctor.
Okay, good. Good. So at a depth of around 3 meters beneath the earth's surface within the landfill, you have the concentration here to be the methane concentration of this to be 20 milligram per liter. Milligram per liter, you know, is ppm, parts per million. Okay? And then in the air, the atmospheric concentration, so that's in the air, okay, or on the surface here, where the concentration is 4.87 ppm, which is milligram per liter. So there is difference in concentration. So the methane will move from region of higher concentration to region of lower concentration, isn't it? So it will diffuse up. Okay, there will be diffusion. Okay, because there is concentration gradient that is created here. Okay, so what is that gradient? And the distance is 3 meters. Okay, so the difference. So we have the flux to be minus d del c by del x, and this is going to be del y, isn't it? Okay, that is the distance between the 2 points. Okay, so the change in concentration is from 20 to 4.8, and this is the distance. Okay, so this is the gradient, the milligram per liter. Okay, milligram per liter times meter because of this one. Okay, so we are just converting to milligram per meter cube, changing the liter to meter. Okay, that's why we multiply by this, changing so that we will have a homogeneous unit. Okay, because this is in liter, this is in meter, so we change the liter to meter cubed. Okay, have it in milligram per meter to power 4. So now the diffusion coefficient is a constant which is provided in centimeter square per second. So we are also changing it to meter square per second. We have this in meter to power 4. Okay, and then 1 acre is simply 4,047 meter square. Okay, in meter square also, just to make our units homogeneous. And then we come back to substitute here. Very simple. Okay, minus. Okay, this is the diffusion coefficient, which is d. Then this is the concentration gradient, del c by del y. Okay. Then we will multiply the units out. This is the flux, milligram per second per meter square. Okay, that is the mass passing per unit time per unit area. Okay. Milligram per second per meter square. Okay. And then the rate of transport meaning milligram per second, we just multiply by the area of transfer. Okay, multiply by the area of transfer, because this is per unit area. So multiplying by the area, this is now the rate of transfer in milligram per second from landfill to atmosphere. This is from the landfill, from 3 meters below the landfill to the atmosphere. So the atmosphere is having less concentration of methane, hence there is concentration gradient, and then there is movement of the contaminant from region of higher concentration to region of lower concentration. Is that clear? Okay. Now, still on the dispersive flux, we have the diffusive flux. Okay. In which, we have what is called TLO dispersion. Okay, which occurs in laminar flow in pipes, narrow channels. It is characterized by the parabolic distribution of velocity. Okay, the parabolic distribution of velocity. We know the velocity within a pipe, varies parabolically, okay, parabolic shape, minimum or zero at the boundary and maximum in the midpoint, okay, due to viscosity or shear stress occurring at the boundary. Viscosity is what causes the shear stress, okay, and then the shear stress is maximum at the boundary, minimum at the midpoint for pipe flow, okay. ED or turbulent dispersion results from velocity fluctuations in advection dominated flow fields like channels, rivers, streams, and lakes. ED or turbulent, you have laminar flow in which the velocity is very low, okay, and then you have turbulent flow in which the velocity is very high and there is high level of mixing, okay. Then you have mechanical dispersions which are associated with heterogeneity in the flow field, such as the flow through porous medium. When you have a porous medium, we have seen you have many layers of different soils or aquifers. You can have an aquifer bounded from above and below by an aquitard, and you have different layers, okay, which will affect the flow, okay. So this is heterogeneity. If the soil medium is homogeneous, it means it has more or less uniform properties of porosity and hydraulic conductivity, okay. But more often than not, in practical cases, you have these values changing from place to place, okay. They change from place to place, so that makes the flow field to be heterogeneous, okay. Hetero means you have differences, the characteristics of the porous medium differs from point to point, okay. And the most important characteristics we're referring to here, you have porosity, you have hydraulic conductivity, okay. And then the mechanical dispersion is caused by variation within a pore, okay. Within a pore, there is variation, and there is also variation with pore size. The pore sizes are not uniform, they vary, okay. Unless it is approximated as a uniform porous medium, which more often than not, hardly do you find that. But for idealization, we can take it to be uniform, but you find variation within the pore size, and you have branching, okay, of flow path, okay, branching of flow path, which is the tortuosity, okay. Here, referring to the curved path taken, due to the porous medium, okay. This one will take this one, okay. So different paths taken by the fluid flowing through the porous medium because of the presence of the porous medium, okay. So it will not like flow in a straight line as if you have a pure liquid, okay, without any porous medium, okay. It will be like zigzag, irregular shaped, moving from this angle to that angle. That is the tortuous path, okay. So all this contributes to the mixing effect, which is causing the mechanical dispersion, okay. And then this is called longitudinal dispersion, which is made up of the D subscript D is the diffusion, molecular diffusion plus mechanical dispersion, okay. You have molecular diffusion plus mechanical dispersion or hydrodynamic dispersion. This is DL is sometimes called hydrodynamic dispersion. Hydrodynamic dispersion is made up of molecular diffusion and mechanical dispersion, okay. And these two, when you combine them, okay, this alpha u is the velocity, alpha is called the dispersivity of the medium, okay, the dispersivity of the medium, and u is the velocity, okay. So this component alpha u indicates the mechanical or takes care of the mechanical dispersion, while the first term takes care of the molecular diffusion, because you have tau is the tortuosity factor, okay, which takes, and D naught is the diffusivity or the diffusion coefficient in pure liquid, okay, pure liquid without porous medium, and the tortuosity factor takes care of the presence of the porous medium, which is less than 1. So it's like a fraction. The the diffusion coefficient in a porous medium is like a fraction of the diffusion coefficient in a pure liquid. So this tortuosity factor takes care of that. It's usually around 0.7. Okay, by 0.7 it means the diffusion occurring in porous medium is about 70%, that of pure liquid, that is without porous medium. Okay, so these two, when you add them up together, they give the longitudinal diffusion or the hydrodynamic diffusion coefficient. Okay, but we will not go so deep into this. Okay, except for those of you that may like to take a senior elective in groundwater engineering or groundwater hydrology. Okay, if you take we have a course, groundwater hydrology, in which we will go so deep into the contaminant transport mechanism. Okay, but at this point we will just give you the basics and then move on. Okay, now when you have a source of contamination, okay, which is releasing contaminant into the groundwater flow direction, okay, you can see it will be moving this. Okay, if you are modeling it using advection, it will move like a plug, like in this case, okay, without any distortion. Okay, if you consider dispersion and diffusion, then it will be spread. It will not be like a regular shaped, rectangular, shaped plume. Okay, it will be distorted. There will be some distortion because now you are considering the variation effect of the velocity as well as the concentration. Then we have other factors or transport mechanisms that affect the movement of the contaminant, which we did not discuss, called suction and retardation. Suction, these contaminants, sometimes, most of them, when you have organic contaminants, let's say you have liquid or benzene, leaching from the ground storage tank and reaching the water table and then flowing along with the groundwater. This benzene is organic in nature, and soil has what is called organic content. Okay, OC. All soil has organic, they all have what is called organic content. Okay, which is obtained by heating the soil in an oven at a temperature above 100, like 105 for some hours. Okay, you measure the weight before and after. Okay, and the difference was usually around 3%, maybe 3 to 5%. It depends on the soil type, their origin and all that. So, but one thing for sure is that all soil, they have this. Okay, when you heat above 105, you expel the water, and then when you heat further, you now do away with the organics. Okay, and it's usually about 3 to 5%. So these organics, they are also they are called organic content of soil. Okay, so when you have benzene, which is organic in nature, like materials attract each other, isn't it? Organics will move to organics, non-organics will move to non-organic. Like when you have benzene, that is fuel, and water, they are not going to mix because water is polar, is a polar solvent, while benzene is a non-polar solvent, so they will not mix. But when you have alcohol and water, they are going to mix because they are all polar solvent. Okay, so when you have organic and organic material, they attract each other. When you have organic and non-organic material, they don't usually attract each other. So if the source of contamination is, let's say, benzene, so it will tend to be attracted by the soil grains or the organic that is present, the organic content of the soil. Okay, so it will tend to be attracted, thus retarding or decelerating, the movement of the average forward velocity of the fluid. Okay, because it will try to be like separating from the liquid to get attached to the soil grain, and that is somehow reducing the speed of the fluid. Okay, and that is called retardation. Retardation is simply deceleration. Acceleration is the increase in velocity with time, while deceleration is the decrease, the opposite of acceleration. Okay, so retardation is the same thing with deceleration. Okay, And then depending on the contaminant, they can also get degraded. By degraded here, when you have organics, when your water has dissolved oxygen, dissolved in the presence of organics, in the presence of the organic content of soil, and then the organic material, which is the contaminant, the organic particle or the microorganisms can feed on the contaminant. It will feed on the contaminant in the presence of oxygen, okay, and then convert it to another form or to produce carbon dioxide and water. That is the degradation. Okay, or depending also on the contaminant, it can change from one form to the other in the presence of the dissolved oxygen in water. Water has dissolved oxygen. Oxygen dissolves, although it doesn't, the solubility of oxygen in water is very low, but still it has dissolved oxygen. In fact, that is why when you taste water that is boiled, because when you boil water, when the temperature increases, the solubility of gases in liquids reduces. So you expel the dissolved oxygen. So when you boil water and then try to drink it, you will realize that it tastes flat. It doesn't taste sweet. That sweet taste you feel when you drink water is as a result of the dissolved oxygen present. Okay? So what I'm saying in essence is that water has dissolved oxygen. Okay, it has dissolved oxygen in it, and that oxygen present enable the degradation of some contaminants along the flowing water. Okay, so this is the simple explanation I will provide. I will not go, like I said, into so much details. Okay, because all these they are own flux, which we will add to the advective dispersive equation. Okay, which we will add to the advective dispersive equation. Okay, but at this level, what is most important is for you to understand the simple transport mechanisms, mainly the advection, dispersion, and diffusion. And then, like I said, if you are interested in knowing more on this, then you have the groundwater hydrology course, which you can take, okay, as an elective. And then in that case, we will look at the different transport mechanisms and the mathematical formulations as well as the modeling, okay? In fact, my PhD is specifically in this regard, okay? And here I'm mentioning benzene, okay? It can be heavy metal. It doesn't necessarily mean it is only organic. It can be heavy metal, okay? All soil also, they have inherent heavy metals attached to them, okay? Or trace elements, okay? Trace elements. You can have lead, zinc, okay, mercury, okay, lead, zinc, mercury, and all these can be attached, and then they can be dissolved along the flowing fluid and be carried along the flowing fluid, okay, and all these constitute contamination of the groundwater, okay. And like I said, my PhD specifically is on soil remediation. That is, the decontamination of soil that is already like polluted with heavy metals, organics, and what have you. Let me see what you are saying, because I cannot uh, read your comments while I'm making the presentation. So let me check your comments. Okay, all right. Okay, now we'll move to the next area, okay, which is still under the groundwater contamination, which is the saline water intrusion. Okay, intrude is to like invade, to come uninvited. Okay, like you're trying to close a door and you're trying to push. Okay, that is like intruding. Trying to force yourself into an area that you are not really like invited or wanted. You understand? So that's like the meaning of intrusion. Okay, it's from the word intrude. Okay, so the intrusion of saline water is a common groundwater problem, most especially in arid region or in the Sahara Desert. Saudi Arabia, the Middle East, most of the areas here is Sahara Desert. Okay, you have coastal areas, coastal cities, because they're surrounded by ocean, by seas, which is seawater. Okay, so you have coastal pollution, and this occurs due to invasion of seawater in coastal aquifers. Okay, those coastal cities, so the seawater will have coastal aquifers. Okay, so the seepage of saline waste from the surface and upward movement of saline waters of geologic origin in other aquifers. Okay, that is, in other aquifers, it doesn't necessarily, you don't necessarily need to have coastal aquifers before you can have the saline water intrusion. Okay, you can have saline waters of geologic or in other aquifers. When you go deep down, normally you find saline waters. Okay, that is why, like I told you, most of our boreholes, I mean, the boreholes in various houses, when you taste the water, you realize it is saline because they are obtained at deeper aquifers, sometimes up to 1 kilometer depth. Okay, so at such depth, normally you encounter saline waters of geologic origin. Okay, now let's see the dynamics and what happens between the fresh and saline water and the equilibrium in an unconfined coastal aquifer. Okay, here we are considering an unconfined coastal aquifer. Okay, this is the sea. Okay, this is the sea. Okay, so we know that the saline water is heavier, is denser than fresh water. Its density is higher. They don't normally mix. Okay, so within the aquifer, you have a boundary, an interface. Okay, this is the fresh water and this is the saline water and this is the interface. Okay, if we consider point A lying on this interface, what are the pressure acting? On top, you have the pressure due to the pure fresh water. Okay, due to the fresh water, rho Fg, the height acting Z plus H. H is the height of the water table above, the height of the water table above the sea level. Okay, that is H. And then below it, you have just rho Sg. Let me hide this. Okay, rho Sgz. Okay, because the height of the saline water is, okay, which is Z. Okay, okay, and then this particle is equilibrium. For the equilibrium of this particle, the pressures are acting are equal. So this is equal to this, okay, which is this one. So making Z the subject of the formula here, we have Z to be equal to rho F subscript F for fresh water, S for saline water, okay, H. And when you substitute, let's say for fresh water, 1 gram per centimeter cube, for saline water, 1.025, we'll have Z to be equal to Z equal 40H. Okay, for typical seawater, okay, meaning that the depth to saline water in coastal aquifer is about 40 times the height of the water table above the sea level, okay, which is H, okay, 40 times. Okay, now this equilibrium can be distorted. Okay, this equilibrium can be distorted. Like if you sink the well here, this well is currently sunk into the fresh water. When you pump water here excessively, you are drawing water, and then this boundary, this interface will be moving. Okay, it will be moving inland, inward. Okay, it will be moving because you are reducing the amount of the fresh water. Okay, so it will be moving up to the point when you have seawater in your wells. Okay, up to the point when you have seawater in your wells. Okay, and that is the saline water intrusion. Okay, so the saline water is intruding. It's like forcing itself inland. Okay, so it's forcing itself into the into the coastal aquifer, and then the wells around the areas will now be having saline water. Okay, so that is the intrusion. The next part is upconing of saline water. Upconing of saline water. When a saline water layer underlies the freshwater zone and a well penetrating only the freshwater portion is pumped, a local rise of the interface of saline and freshwater occurs, which is called upconing. Okay, what are we saying in essence? You have saline water deep down. See it here. Okay, deep down, like I said, deeper down, you have saline water of geologic origin. Okay, deeper down. Okay, and then above it, you have fresh water. This is your well, dug at a depth D, separating the bottom of the well to the surface or initial surface of fresh and saline water interface. Okay, and this is called the critical depth. That is the depth within which the interface can rise, because we don't want this interface to rise up to the level of the well. This is the level of the well. So we don't want this interface to rise to this level, because if it does, it means we are going to be pumping out saline water. Okay, so we don't want that to happen. And this is the piezometric surface. Okay, so the water table. Okay, now this depth, this critical depth, is given as Q rho F over 2 pi dk into rho S minus rho F. K is the hydraulic conductivity. Okay, and it has been found that to avoid upconing, you see, when you are pumping, this layer or interface will be moving gradually up, because you are reducing the amount of the fresh water. So you are distorting the balance, the equilibrium, and then more of the fresh water will be pumped or will try to offset the balance. Okay, will try to maintain the same equilibrium by having more of the fresh water, because you are removing the fresh water. Okay, unless of course it is counterbalanced by a particular recharge area where you have the fresh water being injected. Otherwise, in the absence of any input, the saline water will expand to maintain the equilibrium. Okay, so thereby moving the interface gradually. You can see that is upconing. Con is something like this. This is con. Okay, so upconing, it is increasing. Okay, it is increasing. Okay, so when you are still pumping, okay, this interface will be moving up till a point whereby it can move into your well. And at that point, all you are going to be pumping will be saline water. Okay, will be saline water. So to avoid the movement of this interface to this level, that you will be pumping only saline water, this critical depth has to be maintained within certain region, and this is the formula to find the critical depth. And to avoid the upconing effect, Z is 0.5 D, about 0.3 to 0.5 D. Okay, and when you substitute Z equals 0.5 D here, you will find the maximum flow rate. That is the maximum rate at which water can be pumped safely from this well without the interface moving from this level up to the well level. Okay, so this is the safe discharge rate. That is the safe discharge rate, because excess discharge or excess flow rate or pumping of water from well causes saline water to intrude into our wells. Okay, and this is the process, this is the mechanism, this is how it takes place. Okay, the process is called upconing. Now, in a real situation, a zone of brackish water occurs between salt water and fresh water. Brackish is also salt water or sea water, but the concentration of salt in brackish is less than that of sea water. Okay, so it's like the transition between fresh water and sea water. Okay, so you have a zone of brackish water which occurs between salt water and fresh water. But even with a low rate of pumping, some saline water reaches the well. Meaning, even with that, even when you find the maximum rate at which you will pump the water in the previous slide, you still find out that some saline water reaches the well. Okay, and like I said, this explains why most of our um, uh, borehole waters, our well waters are pumping saline waters. Okay, the water, sometimes when you taste water from the tap, you realize that it is terribly saline. Okay, however, the upconing effect can be minimized by decreasing D, that is separating wells from the saltwater layer as far as possible, and decreasing the flow rate. Okay, by decreasing D, okay, meaning instead of digging deeper, you can dig your well to, let's say, somewhere here, as long as you are sure that you will have adequate amount of water. Don't dig deeper. Okay, like I said, here in Saudi Arabia, more often than not, for us to have appreciable amount of water, you need to dig very, very deep. Okay, 700 meters, 800 meters, up to 1,000 meters. Okay, and that is also part of the reasons why we are having, we are going deeper down to the saline water region. Okay, we are going deeper down to the saline water region. Okay, more often than not, the saline water is of geological origin. Okay, so they have been there, just like oil for time immemorial. Just like you are mining oil, you dig deeper, isn't it? You go very to get oil. So the same thing here. You are more or less like mining the water. Okay, because precipitation is very low, very small and not even reliable. So talking about recharge areas is not feasible. Okay, so these waters have been there, for a very, very long time. Okay, so that's why still, if you have water from the wells, you need to treat it. You need to treat it to reduce the, total dissolved solid content. Okay, to reduce the salt content, that is in form of total dissolved solids. Okay, so it has to undergo treatment. And those that do not undergo treatment, when you test them, you will feel from your tongue that they taste very, very salty. Okay, is that clear? Now, a simple example to demonstrate this, you have here example 7.10. In a deep aquifer, fresh water extends to a depth. So here you have a deep aquifer in which fresh water extends to a depth of one. Okay, you have, let's say, the ground surface. So fresh water extends to a depth of 120. Okay, let's say this is 120, 120 feet, fresh water. Okay, below which there is a deposit of salt water of specific weight. So here you have salt water of specific weight, 64 pounds per feet cubed. A water well is drilled through the freshwater zone to a depth of 80. So you have a water well to a depth of 80 feet. So the distance from the bottom of the well to the salt water interface, if this is 80, then this is 40, because it's going to be 120 minus 80. So this is 40 feet, okay, which is equal to our D, isn't it? Okay, determine the maximum rate at which This well can be pumped without drawing saline water from the well if the aquifer permeability is 1,000 feet per day. Permeability is the hydraulic conductivity, okay? So we have K, aquifer permeability here, okay? K to be 100,000 feet per day, okay? So what's the maximum rate at which, as the maximum Q, at which water can be pumped without moving this, without pumping saline water into this well, okay? That is to maintain the saline water interface far below the bottom of the well, okay? We just apply the formula. Okay? This is Q max, okay? And D, we found it to be 40 feet. K is provided. This is density of saline water, density of fresh water, okay? Which we will just substitute. We can use density here as well as specific weight, okay? We can either use density or specific weight, because specific weight is the density of sensor over density of water, okay? So you'll all have density of water, which will cancel out, okay? So you can use either density here or specific weight, okay? And when you substitute, you'll find it to be 1.49 cubic feet per second, okay? But we mentioned even at this rate, you may still have saline water in your well, okay? Because we mentioned that another way is not to dig the well so deep, okay? Okay, not to dig it so deep, but that depends on a lot of other factors, okay? Because it depends on the depth to the aquifer that is having the appreciable amount of water, okay? Because that dictates the depth to which the well can be dug, okay? Any question? Okay, if you don't have any question, we will take like a 5 minutes break and then come back so that we can take the next chapter, okay? So let's take a 5 minutes break. Yes, we are back. Let's move on. Now we'll move to estimation of surface water flow, hydrograph analysis. Okay? And the intended learning outcomes here. Because of time factor, we'll only explain storm runoff hydrograph and the mechanisms of runoff generation. Time will not allow us to go deep into the actual hydrograph analysis, okay, the numerical part on the quantitative part on how the hydrograph analysis is conducted. Okay, it is a very interesting concept. Okay, but like I said, because of the time factor and the fact that it really takes a lot of time, explaining all this. But the detailed part is reserved for another senior elective course called surface hydrology, surface water hydrology. Okay. Anybody interested can take the surface water hydrology, where the hydrograph analysis will be thoroughly examined and treated. Okay. But for water engineering here, dealing with hydrology and hydraulics, we'll just introduce you to the basic concepts and then move on. Runoff and stream flow. This we have already started explaining in chapter 4 under infiltration. Okay. The term runoff is used for water that is on the run. Okay, it is running or in a flowing state. Okay, forms of runoff in the hydrologic cycle. You have rainfall, which is the main input. Okay, main input into the system. Then when it rains, you have infiltration taking place based on the infiltration capacity. Initially, the infiltration capacity is very high, but over time, it becomes constant when it becomes saturated, and then you begin to have surface runoff. Okay, before surface runoff, you have the depression storage, and then you have the surface runoff. Okay, and here you have interception and depression storage. And here, when it infiltrates, it improves the soil moisture, and then deep percolation joins the groundwater, which flows, okay, which also flows as base flow. And at each of these areas, you have evaporation taking place, okay. For the surface water, you have evaporation. For the interception storage, you have evaporation. For the soil moisture storage, you have evapotranspiration, which is the movement, the evaporation transpiration, okay, movement of water through the stomata, the tiny openings at the underside of leaves for plants, okay. And even for groundwater, you still have evaporation because the soil is not like a vacuum. Still, you have atmospheric pressure acting on the water table. So you still have evaporation coming out. Okay. And then the base flow, you have the direct runoff, which can join stream to form stream flow. Okay. Surface runoff will become direct runoff and stream flow. Runoff versus stream flow. Okay. Stream flow is usually obtained by two things: direct runoff and subsurface runoff. These two combine to form stream flow. Okay, the direct runoff is from the surface. Okay, that is the surface water flow. Then the subsurface runoff is from the groundwater flow. Okay, or what is called the through flow or return overflow. This we will explain later. Okay. Yeah, it's even here. You have the direct runoff, from the surface runoff or over land runoff. Okay, then you have the subsurface runoff constituted of the interflow, through flow, subsurface storm flow, and the base flow. Okay, and streams. First order basin. Okay, stream orders. Okay, you see, this is the initial one. Okay, this is the initial one. joining 1, you can see joining to give 2, okay, 2 and 2 joining 3, 3 and 3 joining into, into 4, and then this 4 is the one draining the area, okay. You can have even 6 or higher order basin, okay. So this is a 4 order basin, okay. We call it a basin, a catchment or watershed, okay, which is an area of land, that is being drained, that is draining into by a given outlet, okay. So this is the only outlet. You have it here, isn't it? And this is like a river or stream, so it will drain. The river will drain into a stream or another bigger river, okay, and then the water flows, okay. But this catchment or this basin is being drained completely by this one, okay, by this number 4, okay, because everything else drains into it, okay. And this, like I said, you can have 6 or higher order basin. This is a 4th order basin. Now, hydrograph. Graph showing the rainfall. Okay, a plot of stream flow, that is discharge against time at any section of a stream or channel, is known as hydrograph. Okay, that's why we look at the order of the stream. Okay, at any point, because water is flowing. Okay, at any point when you plot the discharge versus time. Okay, so you measure the discharge over time, over some interval, and then when you plot it, that gives the hydrograph. Okay, and there are 2 general approaches to prepare hydrographs from runoff data. Okay, you have the first one called unit hydrograph and flow routing. Unit hydrograph is simply like an idealization, okay, whereby you assume that you have rainfall of unit magnitude, okay, occurring in unit duration and causing a unit amount of runoff. Okay, so you have a rainfall, let's say, of 1 centimeter occurring in unit duration, let's say 1 second, and then that rainfall is applied uniformly over the basin and is causing unit amount of runoff. Okay, so that's why we call it unit, because everything will have unit there. Okay, so if we can have this hydrograph, the runoff generated by this unit amount of rainfall in a unit duration, then we can translate it into, we can derive another runoff of another duration. If you have 2-hour storm or any other hour storm from this unit hydrograph, okay? And then you have flow routing. Like I said, these are more detailed concepts that time will not allow us in this course to go into the details of the unit hydrograph, okay, and flow routing. However, probably we will see what will happen, let's say, in the lab to see if we can design another experiment with what we currently have, okay, to demonstrate the simple application of the unit hydrograph. Now, mechanisms of runoff, okay, mechanisms of runoff generation. This we started discussing in chapter 4. Although in chapter 4, we looked at the Houghton overland flow, where we looked at the Houghton's equation, isn't it? Houghton's infiltration equation, which is F, the infiltration capacity given by the initial infiltration capacity minus the constant one exponential minus KT plus F plus FC, isn't it? But this is part of the question that you did, okay, in the major 1 to find the total amount of water infiltrated. The formula was provided, is just to substitute and get the answer. Okay. So this is the Houghton overland flow, and what does it postulate? Okay, the classic concept of Houghton, okay, holds that any soil surface has a certain maximum rate of water absorbance. It has a certain maximum rate of water absorbance known as the infiltration capacity. Okay, and this capacity, so this is the infiltration capacity, and this capacity, it high at onset, okay, which is F naught, that is the initial infiltration capacity. It is high at onset, okay, of rainfall, and then declines rapidly. It declines rapidly to achieve a constant rate. Okay, so here, if you remember our plot, we have something like this, okay, over time. Okay, this is the infiltration capacity. So initially it starts at high rate, and then over time it decreases to a constant rate, which is FC. Okay, it decreases to a constant rate FC. If rainfall intensity at any time during a storm exceeds the infiltration capacity of the soil, water accumulates on this. If the rainfall intensity is greater than the infiltration capacity, it accumulates in the surface and fills small depressions and runs downslope as overland flow. And this we explain that if the rainfall intensity is less than the infiltration capacity, it means it will infiltrate. Okay, it will infiltrate until to such a level that it reaches the constant infiltration capacity, and that is when you will begin to have runoff. Okay? And according to this theory, the major contribution to direct stream flow is overland runoff. Okay, overland runoff contributes to stream flow because it will end off in stream or river. Okay, recognized as the Houghton overland flow, shown as path 1 in figure 9.2. We are going to check figure 9.2. Okay, so let me quickly check it and then come back. This is figure 9.2. Okay, this is path 1 for Houghton overland flow. Okay, when you have rainfall, it infiltrates up to when it will reach the infiltration capacity, the maximum infiltration capacity of the soil, and then you begin to have runoff going, okay, into the stream to contribute to the stream flow. Practically, the entire basin area contributes to this overland flow, and Houghton's runoff serves as a base for the unit hydrograph technique and the infiltration curve technique. Houghton's theory has applicability in arid and semi-arid landscapes. Okay, like the Middle East, when we have the arid, where we have the arid regions. Okay, and North Africa as well, and semi-arid landscapes and cultivated fields, paved areas, and construction sites and rural roads of humid regions that lack a dense vegetation cover and well aggregated topsoil. So these are all the areas that the Houghton's theory has wider application. Okay, we are going to discuss basically 3 mechanisms of runoff generation. The second one, postulated by Hewlett and Hibbert in 1967, and also Catby and Chole and others suggested the theory of subsurface storm flow or through flow. Okay, according to this, a densely vegetated humid region. Humid means you have high humidity. Okay, vegetated means you have many plants like grasses and what have you. So you have many grasses densely, closely packed together. That's what, okay, densely. And humid means you have probably a lot of rainfall. Okay, because sometimes like coastal areas in which you have humid, the humidity is usually high in coastal areas. Okay, it has the capacity to absorb all except the rarest, most intense storms. Okay, so here it's postulating that these areas will absorb most of the water, most of the precipitation, except the rarest and most intense storms. Major part of this absorbed water moves laterally through the shallow soil horizon in the zone of aeration, shown as path 3 in figure 9.2. So here, let's go to figure 9.2, path 3. So here it's saying that it will absorb most of the water except the rarest and most severe storm, and then it will flow just beneath the earth's surface in the zone of aeration. Okay, and then it may come out as through flow and then join the stream flow. Okay, so this is the second mechanism. The third one, this through flow. Then the third one here is discussing about The third type of storm runoff for humid regions is based on the concept of saturation over land flow. Okay, and here rainfall causes a thin layer of soil on some parts of a basin to saturate upward from some restricting boundary to the ground surface, especially in zones of shallow, wet, or less permeable soil. And the runoff cannot infiltrate further in the saturated soil and runs over as the saturation over land flow. So what we are saying is that it first saturates some few depths from the ground surface into the soil, and then before you have saturation over land flow, and some water moving through the topsoil also appears as the return flow. Okay, so this is shown in path 4. This is path 4. Okay, for path 3, it doesn't talk about, it talks about the flow flowing under the soil and then joining the stream. But for path 4, it talks about the flow from the beneath the topsoil and then coming out as through flow. Okay, it is coming out again and then as oval as it joins the surface runoff. Okay, what is called the return flow. Okay, so this is the return flow, and this is through flow. The through flow is flowing just through it. Okay, it's flowing beneath the earth surface and joining the stream, while the fourth one is flowing in the subsurface and then coming out as return flow to join surface runoff before it finally join the stream. Okay, if you look at all these three, they are basically in a nutshell trying to say the same thing in one way or another. They are so much related in the sense that you have infiltration taking place, you have subsurface saturation to some extent before you have surface runoff, okay? With some postulating that runoff occurs in the subsurface below the topsoil, okay? And the conditions controlling the runoff mechanisms, okay? These are the different conditions controlling the runoff mechanisms, depending on climate, vegetation, and land use. Okay, arid to subhumid, arid region, that is areas where you don't have rainfall, the Sahara region. Okay, the Sahara desert area. Okay, these are the arid region. Arid to subhumid climate, thin vegetation, and in arid regions, you have low humidity, then you have very low precipitation, okay, and all that. So arid to subhumid climate, thin vegetation, okay, and then here you have humid climate, dense vegetation. Humid, like I said, is when you have high humidity. Okay, so Horton overland flow dominates hydrograph. Contributions from subsurface storm flow are less important. Okay, and here you have direct precipitation. For the arid region, you have this dominating. For the humid climate dense, you have the direct precipitation and return flow that are dominating the hydrograph. Okay, so all these are the different components of the three mechanisms and the specific areas of dominance. Okay. So on the hydrograph analysis, estimation of stream flow. The stream flow hydrograph is a result of the runoff processes. This is very important. Is as a result of the runoff processes, because the runoff will ultimately, reach the stream and contribute to the stream flow hydrograph. Okay. And overland flow, interflow, and base flow that are generated by precipitation of storms. Okay, because these are the runoff processes. Okay, overland flow, interflow, and base flow that are generated by precipitation storms. okay, which is rainfall. Okay, rainfall, we call it precipitation, we call it storm, okay, what have you. The hydrograph resulting from a precipitation storm is known as a storm hydrograph. Okay, and stream flow hydrograph is thus the cumulative effect of storm hydrographs, because the stream collects the water that resulted from precipitation, isn't it, over time. It precipitates, I mean, the land now, depending on the topography, transports the water, as surface runoff, and then it ends into the stream. Okay, and then at a particular point in the stream, you can now measure the flow rate versus time to form the stream flow hydrograph. Okay, so the stream flow hydrograph is thus the cumulative effect of storm hydrograph. Cumulative meaning you sum it up. Okay, you sum the storm hydrographs. Okay, that's cumulative. And the simple storm hydrograph is this: you have discharge versus time. Okay, so you have the rising limb, you have the crest, and the recession limb. Okay, we will explain each of these regions. Rising limb. There is a rising limb where the shape of this is characterized by the basin properties. Okay, the shape of the rising limb is characterized by the basin properties and the duration, intensity, and uniformity of the rain. Okay, the duration of the rain, okay, the intensity of the rain, and the uniformity of the rain. All these characterize the rising limb. And then we have the crest segment, which includes the part of the hydrograph from the inflection point on the rising limb to an inflection point on the recession limb. So it's the one connecting the rising and the recession limb, okay, the crest, okay, and it contains the peak flow rate, because normally rains occurs in such, it started with low intensity and then the intensity increases to maximum and then it decreases. Okay, so that point when you have the highest intensity, okay, will usually correspond to the point when you have the crest segment. Okay, and then it contains the peak flow rate. Okay, this I mentioned, and the peak represents the arrival of flow at the outlet from all parts of the basin. Okay, from all parts of the basin. This we are talking about the storm hydrograph. Okay, and the end of the crest, known as the inflection point, marks the end or the time when direct runoff from the overland flow into the stream outlet ceases. Okay, when there is no longer direct runoff coming from the overland flow. Okay, so when it stops coming into the stream outlet. Okay, so you have the inflection point. So what are we saying? You have the rising limb. Okay, okay, the discharge will increase and then reach maximum, then decrease and then stop, because it doesn't or remains constant to some minimum point. End of the crest segment, known as the inflection point. Okay, I explained this. I explained the inflection point. So we have the rising limb, the crest segment, and the inflection point. The crest segment is the one connecting the rising limb to the inflection point or recession limb. The recession limb indicates the storage contribution from detention storage. Okay, it indicates the storage contribution from detention storage. That is depth of water built up over the land surface, because the land surface is not just flat. You have some depression, some like holes, let's say holes, where water can be collected. Okay, these are the depression storages. Okay, the depression storages. So the depth of water built over the land surface. And, okay, the interflow and the groundwater flow. The first step in the hydrograph analysis is to separate the best flow and direct runoff hydrograph. Okay, the best flow and direct runoff hydrograph. And how do you do that? You do it this way. You have the discharge, hydrograph. You have the rising limb, the crest, and then the recession limb. Okay, so when you join the point here, this is the separation line. This is the base flow. okay? And this is the interflow, and this is the saturated overland flow, okay? I will just show it. Time will not allow us to go into the quantitative analysis, okay? But basically, this is how it is done. You can just use a graph paper to just join the points and calculate the area here, okay? You find the area, you deduct, and then the area here gives the total area of the direct runoff, okay? And this is the interflow, okay? Any question? Okay, so now, okay, in the absence of any question, we will move to the next chapter. Let me share the slide. Don't forget, today we have lab, okay? We'll look at the groundwater hydrology, okay? We'll also determine the hydraulic conductivity using, our groundwater hydrology system. Okay, let me put it in the presentation mode. All right. Now, here to hydrodynamic equations of flow. The hydrodynamic equations of flow, and here the intended learning outcomes. We have students will be able to, at the end of this presentation, derive and apply continuity, energy, and momentum equations to open channel flow. Okay. Okay, derive and apply continuity, energy, and momentum equations to open channel flow. Most of these equations have been introduced in fluid mechanics. Okay, here we'll apply them to more specific water engineering problems. Okay, hydrodynamic equations. What is hydraulics? Okay, there are three hydraulics we explained before, as the study of, fluid, okay? And the forces acting on fluid together with their application, okay? Okay. when we say fluid in this case, or for civil engineering in particular, we are referring to the discharge as well as the fluid properties and the flow properties, okay, how the flow properties are affected, okay, in the course of fluid flow. Okay, so all these constitute what we are going to do in hydraulics. And water engineering, like I mentioned before from the beginning, consists of hydraulics and hydrology. Okay, we have finished dealing with hydrology. We looked at surface hydrology. No, we looked at the hydrology and we looked at groundwater hydrology. Okay, we looked at groundwater hydrology, and now we will begin to look at hydraulics. Okay, all we did up till the last chapter is on surface and groundwater hydrology. Okay, the last chapter we just concluded now about the unit hydrograph is on surface water hydrology as well. Okay, right, and then we did groundwater hydrology. So all we did was hydrology from the beginning until now. So this is where we are going to start with hydraulics. Okay, and most of the things we are going to discuss here, some of them we already laid the foundation in fluid mechanics. Okay, so we will look at some deeper treatment and more applications with respect to even design examples in some instances. Okay, some simple design problems that we are going to consider here. So there are three basic hydrodynamic equations that can describe all types of flow problems in hydraulics, because hydraulics we are dealing with flow, and all the properties of flow, okay, or all the properties, of the flow that is being that changes over time, okay, that changes over time or that becomes affected, okay. So there are three basic hydrodynamic equations that can describe all types of flow problems in hydraulics. And these are the continuity equation, energy equation, and the momentum equation. Okay, we will take each of them and then see what they entail. Like I said, we had some idea about what they mean. I mean, we discussed some of them in fluid mechanics. The combined application of the continuity and energy equations, or the continuity and momentum equation, is common to hydraulic problems. Okay, more often than not, you have to combine more than one. Okay, the continuity and energy equation, the continuity and momentum equation. Okay, you have to combine more than one equation in solving a given problem in hydraulics. And the combination of the continuity equation and the momentum equation is known as the St. Venant equations for one-dimensional analysis of unsteady state flow. Okay, so this is like a very famous equation called St. Venant equations for one-dimensional analysis of unsteady state flow. Okay. The momentum equation accounts for all forces in a hydraulic system. It is distinct from the energy equation since energy is a scalar quantity, whereas momentum is a vector quantity. So here we deal with, energy is a scalar quantity, momentum is a vector quantity. So here we'll involve some magnitude and direction, while for energy equation, have nothing to do with direction in that case. And in certain problems, both lead to similar results. Sometimes applying the two equations independently will yield the same result. In other problems, only one of them can be used conveniently. Okay? We will take some examples and then we will demonstrate all this. The energy equation is simpler to use and has a wider application. Okay? Simpler to use and has a wider application. Okay? Now, we'll start with the continuity equation. Okay, the continuity equation originates. It originates from the law of conservation of mass. Okay, law of conservation of mass, and to develop a continuous form, we consider an element of fluid. Okay, volume shown in figure 9.1. Okay, this is figure 9.1. So we consider an element of fluid flowing. Okay. The figure QL is the lateral flow rate per unit length of channel. Go to the figure. The lateral inflow rate per unit length of the channel. This is the inflow. You can see it. 2 subscript L. Lateral inflow rate per unit length. Per unit length of the channel. Q and A are initial discharge and cross-sectional area. All variables are functions of time and space. Okay, so you have the discharge here. This is the area. Then after time t, after it traverses the distance delta s, it becomes a plus del s, del a del s times delta s. Okay, so like an increment. Okay, in the flow rate, in the as well as the area. This is the slope of the channel, theta, okay, given by S1 to S0, what is called the channel slope. So what is the total inflow? If you look at the total inflow, we have Q here and we have QL. Okay? This is the total inflow into the system, okay? So Q, and this is per unit length. QL is lateral inflow per unit length. So that's why we are multiplying by the length, delta S, to give the total inflow. Okay. And then the total outflow is simply this. Okay. This is the total outflow. Now, the rate of change in volume stored within the element is equal to the change in cross-sectional area multiplied by the length of the section. Okay. Now, what are we saying? The rate of change of volume stored, okay, will be dA dt times ds. S is in length. This is so here we will end up L cube over T, which is flow rate, isn't it? Okay. So dA dt times ds. Okay. So this will give us the rate of change in volume stored within the element. Okay. And according to the conservation law, okay, input minus output equal rate of change in volume. You remember even in our hydrology, delta S equal I minus O, isn't it? Inflow minus outflow gives the change in storage. Okay, so the same thing here. Input minus outflow, output gives the rate of change in volume. So we now have this is our I, this is our O. Okay, and this is the rate of change volume is our S here, isn't it? Okay, we just bring them here and plug them into this equation. Okay, and substituting the inflow and outflow quantities and dividing by delta S, we end up, so we'll substitute here and divide by delta S. As you can see, delta S is common. Okay, so when we divide by delta S, we will have Q plus 2 over delta S plus QL. Although this is minus, okay, let's just do it here. I Q plus QL delta S minus outflow, which is Q plus del Q del S delta S is equal to del A del T delta S. Okay, so let's divide throughout by delta S. Q will cancel Q here, isn't it? And then we divide throughout by delta S. This will cancel, this will cancel, and then we will have just QL minus del Q del S be equal to del A del T. Okay, and this is exactly what we have. Okay, when we make QL the subject of the formula. Okay, so this is the lateral inflow, and since Q is equal to AV, flow rate is area times volume. Okay, we can now substitute instead of using Q here, you can use AV. Okay, but when we use AV, we have to use the product rule. We have to use the product rule. Del by del S AV. We use product rule. You A del V del S. Keeping one constant and differentiating the other. Giving the other constant and differentiating this, isn't it? Del S. Okay, so this is exactly what we have. So this is the expansion of this one here. Okay, using the product rule. Now, this is the continuity equation. Okay, this is the continuity equation in differential form for incompressible flow. We say it's incompressible because most liquids do not compress under the action of pressure. Okay, they do so, but negligible. I mean, their compression is so negligible. Okay, so we call them incompressible. Almost all liquids. Okay, for a very wide channel or for overland flow, area can be substituted by depth. Okay, because for wide channel, you know, for very wide channel, when you have B to be very wide, so you can substitute the area can be substituted for depth, okay, which is Y, or by pressure head, which is H, okay, for a pressurized system. Let's say you have flow in pipes, okay, or system under pressure, like confined aquifer that we have looked at before. If flow is steady, we have the ADT equals 0. For steady flow, the area doesn't change with time because steady flow implies that the flow properties do not change with time. And these flow properties include the cross-sectional area, the velocity, all these do not and the flow rate do not change with time. Okay, so for steady flow, the ADT equals 0 because you have a function time here. And where the water does not run in or out along the course, you have QL be 0, meaning you don't have any input. Okay, from the top, you don't have lateral input coming. Okay, so QL equals 0. And we can now simplify the equation again, which is 9.1 can now be simplified. In this case, dq equal 0 or q equal constant, because q will become constant for steady flow. The flow rate remains the same. It doesn't change with distance. So q1 equals q2. Okay, so the qds becomes constant, which is 0. Sorry, the qds becomes 0 because q equals constant, and thus in discrete terms, and q equal constant. If it is constant, we have q to be equal to AV. Okay, so if it is constant, it means A1 V1 equal A2 V2. But this is a special case for steady flow. Okay, for steady flow in which the flow parameters or properties doesn't change with time. Okay, V is the velocity at two sections, and A is the cross-sectional area at two sections. Okay. We'll stop here, and then in the next class we'll look at the energy equation. Okay. Any question? Any question before we call it a day? All right. See you at the lab. No, for the lab, we go to the water lab, 0507, water engineering lab. Okay, that's where we are going to meet. And be there at 2. We are going to start exactly at 2. Yeah, 0507. be there at 2, and the second batch should be there at exactly 220. The group 2 should be there at 20. Okay, 220, not 230. Okay.